Some chemical reactions, like fireworks, happen very quickly, while others, like rusting, occur very slowly. Chemical kinetics is the area of chemistry that deals with the speeds or rates of reactions. The rate that a chemical reaction proceeds at depends on a few factors. The first being the physical state of the reactants. The more easily the reactants come together, the faster the reaction. When reactants are in a different phase, say a liquid and a solid, the reaction will only proceed at the point of contact. If we smash that solid into 1,000,000 pieces, we've increased the surface area that's available to make contact, so our reaction will proceed more quickly. When reactants are more homogeneous, like a liquid and a liquid, they can mix more easily, increasing the amount of contact between the reactants and increasing the rate of the reaction. The second factor that affects the rate of reaction is the concentration of the reactants. For many reactions, the more stuff you have, the more collisions between them, the faster the reaction will proceed. Here's an example of steel wool that's heated in air versus steel wool being heated in an oxygen-enriched environment. The third factor that's going to affect chemical reaction rates is temperature. As temperature increases, it's because of an increase in kinetic energy. The faster the molecules move, the more they collide, and with more energy, leading to increased reaction rates. The reason that we store food in the refrigerator and freezer is to slow these molecules down, thereby slowing down the reactions that cause food to spoil. And finally, presence of a catalyst. Remember that for any type of chemical reaction, there's a certain amount of energy that must be present in order to make those molecules be in the right orientation in order for them to react with each other. And that energy is called the activation energy. And so catalysts then speed up the reaction by lowering the activation energy needed for the reaction to occur. And catalysts speed up the reaction by lowering the activation energy without being used up or consumed during that reaction. Enzymes are protein molecules that are biological catalysts that are responsible for increasing the rate of some reactions in the human body. If the speed of a car is 60 miles an hour, that car travels 60 miles in 1 hour. The speed of a chemical reaction is its reaction rate. It's the change in concentration or molarity of either the reactants or the products per unit time, usually in molarity per second. Let's look at a hypothetical chemical reaction where A produces B. We start out with only A present, as noted by the red spheres. As the reaction proceeds, after 20 seconds, you see that we have less of A, less of the red spheres, as more of the blue spheres or product B is produced. And after 40 seconds, even more of what we started with, reactant A, has become our product, or B. Notice that the sum of concentrations is still equal to 1 mole. That's because for every mole of B that is produced, 1 mole of A is consumed. We could express our reaction rate by looking at the disappearance of a reactant over time, or we could look at it as the appearance of product over a period of time. In our hypothetical reaction, if we wanted to look at the average rate of the disappearance of our reactant A, we would express that mathematically as A negative, since it's disappearing, change in the concentration of our reactant A divided by the change in time. We can also relate our rate of reaction as the appearance of our product, in this case B, expressed mathematically as, this time a positive value, since this is appearing, the change in concentration of B over the change in time. Here's an actual chemical reaction between butyl chloride and water producing butyl alcohol and hydrochloric acid. And you can see, as time progresses, how the concentration of the butyl chloride decreases until it's completely consumed. And look at what happens to the rate of the reaction over a period of time. As time goes on, the rate decreases as the concentration of our reactant decreases. Less molecules available for the reaction to proceed. If we plotted that data, those changes in concentration over time, we'd get a curve that looks like this. And if we took the slope of a line that's tangent to that curve, that would allow us to determine what the instantaneous rate at any particular time throughout that reaction would be. As reactant gets consumed in a chemical reaction, the reaction rate tends to slow down. So the best indicator of the rate of the reaction is going to be at the beginning of the reaction. If we look at the stoichiometry of this reaction, we have a 1-to-1 ratio between the butyl chloride and the butyl alcohol. And so our butyl chloride is going to disappear at the same rate as our butyl alcohol is going to appear. And so we will express that mathematically as the disappearance of the butyl chloride, shown as disappearing with a negative sign, as being equal to the rate of appearance of the butyl alcohol. If the ratio is not 1-to-1, as in this equation, where we have 2 moles of hydrogen iodide forming 1 mole of hydrogen gas and 1 mole of iodine gas. Since this is a 2-to-1 ratio, and a 2-to-1 ratio with the iodine as well, then our reactant is disappearing twice as fast as the hydrogen gas is being produced. The hydrogen iodide is also disappearing twice as fast as the iodine is appearing. So mathematically, we would express that as showing the disappearance of the hydrogen iodine, first of all, as being a negative value because it's a disappearing, multiplying that by 1/2. This allows us to relate the disappearance of reactant to the appearance of product so that we can get the average rate of the overall reaction. So then, for the generic equation, the rate would be given as, starting with our reactants, which are disappearing, we have a -1 over the lowercase a, which is the coefficient in our generic equation, times the change in concentration of our uppercase A over the change in time, which is going to be equivalent to 1 over our coefficient for B times the change in concentration of B divided by the change in time. And so these are our reactants that are disappearing, and those are going to be related to our products that are appearing as, first of all, a positive value because it's appearing, so 1 over the coefficient for C times the change in concentration of C divided by the change in time, which is going to be equivalent to 1 over the coefficient for D times the change in the concentration over D divided by the change in time. One way we can study the effect of concentration on the reaction rate is to look at the way the rate at the beginning of the reaction, or the initial rate, is dependent on the concentrations at the beginning of the reaction. So if you take a look at this reaction, We could determine the rate of the reaction by looking at the amount of water that's formed, or we could look at the amount of nitrogen gas that's formed. And since stoichiometrically the nitrogen is equivalent to the nitrite and the ammonium ion because they're all a 1-to-1-to-1 ratio, the easiest way would be for us to take a look at the amount of nitrogen gas that's produced. So let's take a look at what happens between two different experiments using this chemical reaction. In the first experiment, we have 0.01 moles of ammonium ions, and in the second we have 0.02. So we have doubled our concentration of ammonium between experiment 1 and experiment 2. The concentration of the nitrite is held constant. So I know that any changes in rate are going to be because we've changed the concentration of the ammonium, since this has stayed the same. And what happens is, by doubling the concentration of ammonium, we have in effect doubled the rate of the reaction. Now let's take a look at what happened between experiments, 4 and 5. Since the ammonium is held constant between these two, then the change in rate is because of the change in the nitrite ion concentration. And between experiments 4 and 5, we double the concentration of nitrite ions, and the rate also doubles. So if we look at experiments 1 and 2, holding nitrite constant, doubling the concentration of ammonium doubles the rate. So we know that the concentration of ammonium is going to be proportional to the concentration of ammonium. And just as we looked at 4 and 5, ammonium constant, nitrite doubling, rate doubling, we know that the rate is also dependent on the concentration of the nitrite ions. And we can express the way that rate depends on the concentration of the reactants, ammonium and nitrite, in terms of the following equation. And this is called a rate law. And K is a rate constant. Rate laws show the relationship between the reaction rate and concentration of the reactants. And the exponents tell us the order of the reaction with respect to each reaction. And since in our rate law that we wrote in the previous slide, we have presumed exponents of 1 in both instances. So we would say that the reaction order is first order to the ammonium and first order to the nitrite. And we can determine the overall reaction order by simply adding the exponents. And we said that they were going to be a presumed 1 in each case, so this reaction would be second order overall. So to sum up the order of the reactants, if changing the concentration of the reactant does not result in a change in rate, then the reaction order is 0 for that reactant. In that case, it would be left out of the rate law. If doubling the concentration results in a doubling in the rate, or tripling the concentration triples the rate, then the reaction order is first order for that reactant. And finally, if doubling the concentration results in the rate quadrupling, or if you triple the concentration, the rate increases by a factor of 9, then we would say the reaction order would be second order for that reactant. Here we have data from 3 experiments where the concentrations of the reactants are varied, and you can see that the rate changes as well. And so to determine the effect of concentration on rate, so that we can determine the order of the reaction and the reactants and write a rate law, what we want to do is pick out 2 trials where one of the reactants changes and the other one is held constant. So if we look at reactant A, in experiment number 1 and experiment number 3, we have 2 different concentrations for A, but the concentrations for B in experiments 1 and 3 are held constant. So I know that the changes in the rate between experiments 1 and 3 then are due to the change in concentration of A. And since my concentration has doubled in experiments 1 and 3, and my rate has increased by a factor of 4. Since that rate is proportional to a squared, then the reaction is second order in A. Now we want to look at the effect of changing the concentration of reactant B on the rate. And so we need to find the two experiments where B changes, but A is held constant. So we will take a look at experiments 1 and 2 in this instance. A is held constant, but B doubles. And the rate changes not at all. And when changing the concentration has no effect on the rate, then the rate law would be 0 for that reactant, in this case, B. And so when we write our rate law, it's going to be, but since reactant B has no effect on rate, then our rate law would actually be thus.